So let us resume. Using the work energy theorem, find the expression for the maximum height. That is our first task. Using the work energy theorem, what we have to do, we have to find the maximum height relation. So the presence of energy at each point we have discussed properly in this part, that at which part what will be the type of the energy. So I want to use some free space at the end. It will be good for me. Okay, here. Yes. Such type of modular very good for me.
Yes.
Okay. So again, just I need to redraw the diagram to mention the proper type of the energy. At this point, it is having the both type of the energy, and only the horizontal component of velocity is equal to V naught cos of theta. And at this point, it is having some height that is considered as a ym. Then it will have some potential energy. At this point, we can consider that it is having both type of energy, potential energy plus kinetic energy. While at the initial point, just after throwing the ball, it is having only the kinetic energy. So according to the law of conservation of energy, energy at the point of projection is equal to energy at the point of projection at the point of projection okay, is equal to energy at maximum height. At maximum height. Okay, fine. Initially, as it is, we can write it, sum of the potential energy less kinetic energy initially is equal to sum of the potential energy, kinetic energy at the highest point. As mostly we use the relation for the potential energy mg, as initially there is no height, so we can replace here 0 plus kinetic energy half mv square. And finally, it is having the height ym, you can see, then our potential energy will become mg, as the height is ym, so I'm writing here ym, plus its kinetic energy is half k or half m, as here the only component is horizontal component, so I will use it v naught cos theta instead of that. Then our relation will become v naught square cos square theta. And I can write this equation half mv square is equal to mg ym plus half m v naught square cos square of theta. And in this complete equation, you can see mass can be cancelled because it is existing in this whole equation. Then our equation will become 1 by 2 v square v naught square is equal to g ym plus 1 by 2 v naught square cos square of theta. And what we need to do, keep in your mind, our target to solve this work energy equation to find the relation for the maximum height by using the work energy theorem here we are using. Okay, fine. So I want to rearrange this equation. I want to move this term on the other side. As a result, it will become negative half v naught square minus 1 by 2 v naught square cos square theta is equal to G y m. Okay, half v naught square is actually the common in this equation. Then after taking common, our relation will become half v naught square into 1 minus cos square theta is equal to G y m. It is cos square theta. Also, from the trigonometry, we know a formula sin square of theta plus cos square of theta is equal to 1. Also, I can write this formula sin square of theta is equal to 1 minus cos square of theta. Then what should I do? I can replace this by sin square of theta. Then our equation will become 1 by 2 v naught square sin square theta is equal to G y m. And as we need the height, so I need to isolate the height. Then our equation will become v naught square sin square of theta divided by 2g. So it is actually the same height that in case of the projectile motion we calculated. But here we have used a different method, that was actually the energy conservation method to calculate the relation for the height, that is actually the final. Okay. So let us check the next demand in this energy part. Okay, here next demand is part 8. What is the time interval del T required to reach the maximum height? Here we have to calculate the time interval to reach the maximum height. For that purpose, we need to remind our equation that previously we have calculated. Let me show you. Where is that? Here is that equation that I am using. We have calculated earlier. Okay, so I need to rewrite the relation for the vertical velocity. Vy is equal to v naught sine of theta minus gt. As we are talking about the projectile motion, in case of the projectile motion at the top point, vertical component of Vy is equal to 0. There is the only horizontal component of motion, that is Vx. Already we have discussed, it is not new. So we need to replace it equal to 0. Then our equation will become V naught sine of theta minus gt equal to 0. Then I can write it gt is equal to V naught sine of theta. Then we can write it t is equal to V naught sine of theta by g. It is not a time of flight, it is actually the time to reach maximum height from point of projection to the point of reaching the maximum height. During this time, during this path, the time taken to reach from the point of projection to reach from the maximum height is actually the time to reach maximum height. We have calculated it here. Okay, let us check its next part. Okay, yes, here is the energy equation. If you are able to shoot your legs forward before landing, you should gain extra range, that should be 0.6 meter. Let me show you how. Here he is shooting his legs, you can see. If you will shoot your legs during your jump, then you can also gain an extra range of 0.6 meter. Okay, fine. If we can range, and then we need to solve a problem here. In this problem, what is the range? We have to calculate the range. Possibly cover with an initial velocity that is given to us is 10 meter per second. Speed during this record and initial angle is 25 degree. Initial angle is 25 degree. We have initial velocity V naught is equal to 10 meter per second, and its initial angle theta is equal to 25 degree. What we have to calculate? We have to calculate the range. For the range, we have the formula V naught square by G sine 2 theta. And we need to replace the given values here. Square of the velocity, square of the 10 divided by 9.8 multiplied by sine of 2 into 25 will results. Directly I am here to write the result instead of using the calculator. That is 7.82. 7.82, as we are talking about the range, so we need to write the unit meter range. But in our current case, we have observed that person is enhancing his legs forward, then he will gain extra distance of 0.6 meter. So for that purpose, you need to add that extra distance in this range, 7.82 plus that 0.6 meter. Then you will gain the results 8.42 meter. So we have finally ended our second question. Oh, sorry, first question.
Finally, indeed.
Okay, you need to have a look on it. In the first case, we are actually calculating the value or the formula of the height, maximum height, by using the energy theorem. Initially, already I have told to you, here it's kinetic and potential energy is 0, and here there also again kinetic and potential energy 0. But just after throwing the ball, it is having the only kinetic energy, but instead of in the absence of, or in not gaining the height, its initial potential energy is 0. At the maximum height, it's only horizontal component of the velocity is here, so it is having both kinetic and potential energy here too. So vertical velocity component Vy is 0, horizontal velocity component is V naught cos of theta according to the so the kinetic energy here will become is equal to 1 by 2 mv square. Then putting the values of Vx, then our equation will become 1 by 2 mv naught square cos square of theta. And gain in potential energy at that time at maximum height is this one. So according to a law of conservation of energy, initial energy is equal to energy at the maximum height. 1 by 2 mv naught square is equal to 1 by 2 mv naught square cos square theta plus mgy maximum. Rearranging and simplifying, and finally putting the value of 1 minus cos square theta is equal to sin square theta is equal to, you need to cancel, simplify, isolate the value of the y, so it is final result. Next was the thing that you need to calculate the time to reach the maximum height. For that purpose, at maximum height Vy is equal to 0. So after this solving this equation, isolating the time t, so it is time to reach the maximum height. That is also new, not new thing for us. Next is a problem that is given to us, that is actually the data. V naught is equal to 10 meter per second, theta is 25, g is 9.8. Putting the values, V naught square sine 2 theta over g 10 square multiplied by sine into 2 multiplied by 25, simplifying 7.82 meter. And as he is enhancing his legs just before landing, then we can add this distance in it, and finally its range has become like this, 8.42 meter. Is it clear?
Yes, it's clear.
Okay. So Get ready for the second question.
Is it long?
No, it is not much long as first was.
Good.
If it was in my hand, I will make the question just for a single line for you. It is actually not in my control.
That would be
Okay,
amazing.
okay. Okay, let me just have a space to solve the questions. The notes is I have made, I think, of 32 pages.
Really?
Yes.
That's very long.
Yes, of course. But you know, it is actually an exam.
General?
It is actually an exam. It is not a single module. You need to understand it is actually the selection from those modules already on which we have worked.
Yeah. Do you think it's a difficult exam or no?
No, it is not difficult, but the most important thing is here your common sense will work here. You need to check the statement, and for example, in the dimension analysis, they are not telling us some type of the variable, just is telling us someone is jumping for its range, what can be the necessary. Then we need to understand for range, we have the formula V naught square or G sine 2 theta. So value of the initial velocity and gravity will matter in this case. So we can use these factor to calculate its range formula by using the dimension analysis. Such type of consideration you need to keep in your mind at that time.
Yeah. Like I know dimensional analysis, I think is pretty easy, but then the energy and vector analysis, I still have to work on because that is very confusing to me still. Like I
Yes,
understand when you
because
tell it, it's very easy to understand, but then coming up with it on my own is more hard.
it is also easy, not difficult, but it is much lengthy. To for a student to have a concentration proper on each step is, I think, a little bit impossible.
Yeah.
Because I am a tutor, so I am working. I know what I need to do on the next step, but a student.
Yeah.
Okay, no problem, no problem. It was a time when I was student, so no problem.
True.
Maybe I have already told to you about me. When I was student of the bachelor, then I topped in my college and gained 100 marks out of 100 for the mathematics. But
Wow.
the most important behind that, just in the last 3 months of the exam, I write for the practice almost 20 kg of the pages. Can you imagine? Just
Oh,
for having a practice of the mathematics.
that is very crazy.
Yes. Okay, fine. Without wasting the time, let us move for the question 2, because our stories will not be ended, but it is a time to study.
That was very
Okay.
impressive story.
Okay, thank you very much. When sometime we will have a time, we will discuss on.
Yes.
Okay, this question evaluates the, you can see in the start of each questions, they are actually giving some hints to you. Evaluates your ability to identify the relevant concepts required to explain the observation. From the observation, you need to tell some concepts here. Here we need to also discuss from the graph. We need to also write some formulas, be as concise and complete as possible. Okay, that is not our part. Our first question is here. Consider the following time evaluation of the acceleration of object on 1D line and both position and velocity at time t is equal to 0 being 0. Consider the following evaluation of the acceleration. Here you can see this is a graph representing two things, acceleration and position. And it is actually one-dimensional, not a two-dimensional. What we have to do, draw qualitatively the curve with respect to time, curve of the position with respect to time, justify your strategy. First of all, we need to understand what can be the strategy in this case. Okay, in this case, the horizontal axis is actually representing the time, and this graph is actually representing the acceleration and also position. So our strategy is that we need to, as the graph is not a linear, it is getting changed with the passage of time. We need to divide our time according to this graph. So initially I'm starting from here when t is equal to 0 at this point. And till this point, I'm considering it is t1. Until this point, I am considering it is t2. It will be easy for me according to time to explain each point. To this point, I am considering it is t3. So from t is equal to 0, from t is equal to 0 to t1 during this path, this time. Here, what can we see? Our graph is initially starting slowly and raising up. What can we understand from this? Okay. Now, as it is about the acceleration, about the position, if we are talking about the acceleration, then we are actually talking about a body that is moving. Because without motion, there is not possible for the acceleration. If the body is moving, initially it is slowly moving, then its speed is getting enhanced. As a result, its acceleration is getting increased. And here you can see acceleration is with the passage of time is getting increased till this point. So from time t is equal to 0 to t1, acceleration is positive. First point that we have understood, as the acceleration is increasing, so we can write as it is increasing, so we can say it is positive because it is increasing. If it is increasing, as it is getting raised up, then we can consider its velocity is actually increasing. As a result, acceleration is increasing. So we can say its velocity is increasing, our first part of time. And next, what is next? Next is actually its position. Its position is actually a curved shape that is moving upward. Just let me show you its position by a highlighter. I can't use the highlighter because it will raise the whole value. Let me try. No, I can't. Okay. Anyway. Okay. This red curved shape is actually representing the position of that moving object till this point. It is actually, position is describing that the speed is increasing and it is actually moving upward in a type of the concave shape upward motion. That is actually position during this time period t is equal to 0 to t1. Now let us talk about the second time, that is tenure from t1 to t2. From t1 to t2, as this graph is, here you can see I have zoomed out it. It's this part is straight line, just on the peak. If its top part is straight line, then I'm also from the duration t1 to t2 hitting this straight line. During this straight line, we can consider during this straight line is actually representing that its velocity is constant. Velocity, because if graph will be a straight line parallel to the horizontal, it will show no variation. If it will show no variation, then its velocity will be the constant. If velocity is constant, then what will be the acceleration? You know, rate of change of velocity is actually the acceleration. If velocity is constant, then acceleration is equal to 0. Fine. Then what will be its position in this case? Its position is actually a straight line. Let me zoom it again to show you this straight line. I'm talking about this straight line. Now, can you see it? This straight line on the peak. While the graph I have made here I have shown properly this straight line, you can see. Okay. So its position is x is straight line. And its slope is v of t, because position is actually the slope of v of t. And next time is t2 to t3, last part, t2 to t3, and it is shown here. You can see, just let me change the color. I'm talking about this curved path. As he was saying that you need to draw the graph on this curve, so I'm drawing the graph on this curve. It is representing its position, and it is also representing after gaining a specific peak of the velocity. Now the velocity is getting reduced. If the velocity is getting reducing, then in that case, what will be the acceleration? Acceleration will not be positive. It will be negative. Or you can say it is actually a retardation. Retardation. What is its position? Its position is actually again a curve, but now this concave shape is increasing downward. It is again the curve that was in our first case, but it is actually downward as shown here. X curved downward, concave down as shown here. That was the description about this graph. You need to have a look here.
But isn't it so that the position doesn't go down, even though the acceleration goes down? Shouldn't it be just like straight? Or like
it is not a straight, it is actually a position that we are here to show for that body. And as he is saying that we need to show on the curve, so on the curve its position is actually this curved path that is actually reducing downward.
But his velocity is not negative, so he doesn't move in position backwards, right?
It is actually, you need to consider when you are driving a car and you want to stop, but before stopping you will slow down the car, and here you can consider the slow down position just before stopping.
But doesn't then my position stay where I was? Like I drove the car to this point from here, and then I just slow down, but I'm still here. I don't go back here.
Okay, here we need to show on the curve its position, as if you want to show the direction position on the road, then it will be straight. But if here we have to show or represent the position of that curve, here its position will be on this curve is downward reducing curve.
Like I drew it in red. This is what
So here we have a problem. The diagram below depicts two pucks on a frictionless table. Puck B 4 times massive as puck A. So we can write it. Mass of B is equal to 4 times mass of A. Starting from the rest, in this way we can consider their initial velocities are equal to 0. The pucker pushed across the table by two equal forces. So the forces that are applied on this puck are the same. Our first question is, which puck reach the finish line first? We have to discuss which puck will reach the finish line first. Okay, the possible information is that is given to us is its mass and its initial velocity and the applied force, which is similar. But according to the Newton's second law, we have the relation for the acceleration A is equal to F over m. And as here we can see, acceleration is inversely proportional to the mass. So if we write for acceleration relation for the mass A, then it will become is equal to F over ma. Similarly, for second mass B, A B is equal to F over MB. Instead of MB, I can write it 4MA. Or I can write it 1 by 4 dot this term F over MA represent the acceleration A. I can write it AA. So we can write AB is equal to AA by 4. Yes. In this case, we can see the acceleration of mass B is 4 times, 1 by 4th times of acceleration of mass A. We can say acceleration of A is greater than acceleration of A B. While both are facing the same forces, so we have not disturbed the factor of force here because both are facing the same forces. And one thing that we need to check, as their initial velocities are equal to 0, then our relation for the distance d is equal to v I t plus half at square. As the initial velocity is equal to 0, then it will become relation d is equal to 1 by 2 at square. Okay, so we need to isolate the value of the t because our question is that which puck reaches the finish line first. Actually, he want to ask about the time. So we need to isolate the time, then our relation will become 2d divided by a square root. And it is again showing that time is inversely proportional to the acceleration. If a body is having a higher acceleration, it will take the shorter time to reach. And if a body will have shorter acceleration, it will take the more time to reach. So, as we know, acceleration of object or the puck A is greater than the B, then it will take the shorter time to reach the finish line. So we can consider that object A will take shorter time as compared to object B to reach the finish line. Is it clear?
Yes.
Okay. Our next question is, which puck has the greater momentum upon reaching the finish line? Here we have to discuss their corresponding momentum by using the given data that which puck will have greater momentum. But from the impulse, we have the relation impulse is equal to change in momentum is also equal to product of force and time. So our question is that which puck will have higher momentum. So it is understood for us the puck that is taking more time according to this product and which is having more mass or more, I can simplify, write it according to a Newton's second law, which will have more mass, which will have more time to reach on the finish line, it will have more momentum. We can say about the puck B because it is having the more mass and it is taking the more time to reach on the finish line. But we can prove it of some by using another equation that which will reach on there. According to the work energy theorem, net work done is equal to change in kinetic energy as they were initially at rest. So I am using only final relation half mv square that they have. Work done is product of force and displacement is equal to half mv square. I can modify the kinetic energy term equation as a m square v square by 2 m, and as a product of mass and velocity is momentum, so product of square of mass and square of velocity will make square of momentum p square over 2m is equal to Fd. So here I need to isolate the momentum. P square is equal to 2m Fd, taking square root on the both sides, then our equation will become 2m Fd. And keep in your mind, both are actually having the same distance to be covered. One will cover the D, other will cover the D from the finish line. So D will be same. I'm making this momentum equation for the both bodies. For the first body, PA is equal to square root of 2 MA FD. Similarly, for the PB, we have an equation 2 as mass MA is equal to 4, MB is equal to 4 MA. So I'm writing 4 MA dot FD. As here we are in the comparison of their momentum, so I wanna take their ratio PA over PB over PA. Then similar terms will be cancelled out because this complete term will be cancelled. The only term will be the 4, so I can write it 4, which is equal to 2. So we can write PB is equal to 2PA. If PB is equal to 2PA, then it is clear momentum of the second object is 2 times of the momentum of the first object. If I will remove this proportionality or this constant 2, then I can write this equation PB is greater than PA. So it is clear that momentum of the puck B will be greater than the